The engineers who designed Unit 2 at 3 Mile Island believed they had built one of the safest machines in American industry. They were not wrong about the engineering. What they had not fully accounted for was the gap between how their instruments described the reactor and what the reactor was actually doing. That gap, opening in the early hours of March 28, 1979, would produce the worst accident in United States commercial nuclear power history. The central question this episode traces is a precise one, not whether nuclear power is safe or dangerous in the abstract, but how a system designed with multiple redundant safeguards could still partially melt its own core. The answer sits at the intersection of a stuck valve, a misleading indicator light, and a series of reasonable-seeming operator decisions made under conditions the training program had not prepared anyone to recognize. Nuclear reactors generate heat through a controlled chain reaction inside a core of fuel. That heat must be removed continuously because the fuel continues producing decay heat even after the chain reaction itself is shut down. The cooling system at INES 2 used pressurized water, a primary loop running through the core, transferring heat to a secondary loop that drove the turbines. Keeping the right amount of water at the right pressure in the primary loop was not optional. It was the central requirement. To relieve excess pressure, the plant used a valve called the pilot-operated relief valve, or PORV. When pressure climbed too high, the valve opened automatically. When pressure returned to safe levels, it was supposed to close. The control room received no direct measurement of whether the valve was open or closed. Instead, operators saw an indicator light that showed whether the electrical signal commanding the valve had been sent. A lit indicator meant the close command had been issued. Engineers and operators treated that as confirmation the valve had closed. It was a proxy measurement, not a direct one, and on the morning of March 28th, that distinction became catastrophic. At 4 a.m., a failure in the secondary feedwater system caused pressure in the primary loop to rise. The PORV opened automatically, exactly as designed. The reactor shut down automatically as well, exactly as designed. Pressure dropped. The close command was sent to the valve. The indicator light changed. Operators saw what they expected to see, but the valve had stuck open. Primary coolant was bleeding out of the system through that open valve, and the indicator light gave no sign of it. Because pressure in the primary loop was falling, an emergency cooling system activated automatically, also exactly as designed. But operators, looking at their instruments, saw rising pressure on one gauge and interpreted the situation as too much water in the system rather than too little. They reduced the emergency cooling flow. The reasoning was internally consistent given what the instruments appeared to show. The instruments were telling the wrong story. Over the next several hours, with coolant continuing to escape through the stuck open valve, the top of the reactor core was exposed. Fuel temperatures rose sharply. Zirconium cladding on the fuel rods reacted with steam and produced hydrogen gas. A portion of the core melted. This was a sequence that reactor safety analysis had considered theoretically possible, but that no operating commercial plant had experienced. The training and procedures available to the operators that morning had not been written to help them recognize it. The stuck PORV was eventually identified and closed, more than 2 hours after the accident began. By then, significant damage to the fuel had already occurred. A hydrogen bubble formed inside the reactor vessel, raising concerns in the days that followed about whether it could ignite. Regulatory officials and plant management gave conflicting public statements about the severity of the situation. Governor Richard Thornburgh advised pregnant women and young children within a 5-mile radius to leave the area as a precaution. Approximately 140,000 people evacuated voluntarily. The anxiety in the surrounding communities was real and prolonged, even as technical assessments of the radioactive release itself remained disputed in the days immediately following. Investigations conducted in the months and years after the accident, including the report of the President's Commission on the Accident at 3 Mile Island, found that the radioactive gases and iodine released to the environment were relatively small in quantity Scientific consensus, reflected in subsequent studies reviewed by bodies including the American Nuclear Society, held that the detectable health effects on plant workers and the surrounding public were very low. That finding has remained the scientific consensus, though it has not resolved public distrust, and the accident's psychological and political effects were substantial regardless of the radiological dose delivered. The investigation identified 3 distinct layers of cause. The proximate technical cause was the stuck PORV combined with an indicator that measured command state rather than valve position. The deeper technical cause was that the instrument design made a stuck open valve invisible during exactly the conditions when operators most needed accurate information. The organizational cause was that training scenarios had not prepared operators for a small break loss of coolant event combined with a misleading instrument. Operators followed their training. Their training had not modeled this specific failure mode. The Commission also identified a broader industry and regulatory culture that had not moved quickly enough to incorporate lessons from an eerily similar event. A near-identical PORV failure at the Davis-Besse plant in Ohio in 1977 had been analyzed, but the specific lesson about misleading indicators had not been translated into revised operator guidance across the industry before 3 Mile Island. The ethical dimension was not one of deliberate wrongdoing. It was a failure of institutional communication, a known precursor event, documented and analyzed, whose operational implication had not completed the journey from analyst's report to control room procedure. What changed after 3 Mile Island was extensive. The Nuclear Regulatory Commission fundamentally restructured its oversight approach, moving from a primarily design review model toward ongoing operational safety monitoring. The industry created the Institute of Nuclear Power Operations specifically to share safety-relevant operating experience between plants before incidents rather than after. Control room design standards changed, requiring direct valve position indicators rather than proxy signals wherever critical safety functions were involved. Simulator training was expanded and made mandatory, and the scenarios operators trained against were systematically revised to include the kinds of ambiguous, multi-failure conditions that March 28 had revealed. The accident is rated Level 5 on the International Nuclear Event Scale, an accident with wider consequences. That rating captures both what happened inside the plant and the reach of its effects beyond it. No new commercial nuclear reactor construction was ordered in the United States in the years following the accident. The political and public landscape around nuclear energy shifted in ways that persisted for decades. What 3 Mile Island ultimately demonstrates is not that the engineers failed to build a safe system. The automatic shutdowns, the relief valve, the emergency cooling, each component performed its intended function. The failure was in the information layer, the set of instruments, indicators, procedures, and shared knowledge that allowed human beings to understand what the system was doing in real time. When that information layer gave operators a misleading picture, decisions that were locally rational became collectively catastrophic. The deeper lesson is about the distance between a system's design assumptions and the conditions it will actually face. Every complex engineered system carries within it a set of scenarios its designers considered, and a larger set they did not. The gap between those two sets is not a character flaw or a management failure alone. It is an inherent feature of designing for a world that is more varied than any model of it. What distinguishes systems that manage that gap from systems that are undone by it is the speed and honesty with which they incorporate evidence from near misses before near misses become accidents. 3 Mile Island produced no confirmed fatalities and, by scientific consensus, no measurable increase in illness among the surrounding population. What it produced instead was a transformation in how the American nuclear industry and its regulators understood operational safety. A transformation purchased at the cost of a partially melted core, an evacuated region, and the lasting erosion of public confidence in a technology whose risk profile, the evidence suggests, was neither as low as its advocates claimed before the accident, nor as high as its opponents claimed after it. The question that follows naturally is how other industries that also rely on human operators interpreting complex instrument panels under pressure learned, or failed to learn, the same lesson. That story begins well before 1979 and continues well past it. This content is for educational purposes only. Do not attempt to recreate any described experiment or procedure.